Hey there, it's Shannon Matrick Myers, and today we'll be checking out section 4.6 from the ZIL Intro to Differential Equations text and looking at variation of parameters. So the annihilator method we learned in the last section has two limitations. The differential equation must have constant coefficients, and the input function g of x must be of the type in the table of trial solutions below. So these are just kind of in the midst of, problems you were working, you recognize some of these. So if you have, any constant, you're going to end up having, some a where you're solving for coefficients. If you have something like 3x plus 2, you'd end up with ax plus b. You'd find a and b. 7x squared minus 8, you'd have some sort of ax squared plus bx plus c. X cubed minus x plus 1, you'd have ax cubed plus bx squared plus some cx, and then we'll use e because we used d for differential. If you had a format of sine at 3x, you'd have some a cosine at 3x plus b sine at 3x. And if you had cosine at 3x, you'd actually have the same thing. A times cosine at 3x plus some b times sine at 3x. If you had e raised to the 4x, you'd have an a times e to the 4x. 7x plus 5, that quantity, times e to the 4x, you would have a combination of it, right? So kind of like this 3x plus 2 here, you'd have an ax plus a b. And then from the e to the 4x, you would have all of that multiplied to that e to the 4x is how it would shake out. And then if you had x squared e to the 4x, you would have ax squared plus bx plus c times e to the 4x. And if you had e to the 4x times sine at 3x, you'd have some ae to the 4x times cosine at 3x plus be to the 4x times sine at 3x. And it goes on and on and on. If you had a squared term, you'd now have your, some sort of ax squared plus bx plus c times cosine 3x. And then you'd have to have another quadratic, so call it ex squared plus fx plus g, and that would be times sine at 3x. And if you had some x times e to the 4x cosine at 3x, you would have your ax plus b for the x, e to the 4x, and then cosine 3x, and then plus some cx plus e times e to the 4x times sine at 3x. Cool? All right, so don't worry so much about that, but these are just kind of things that we've sort of were working with before. And in this section, we check out a method for determining a particular solution, yp, of a non-homogeneous linear differential equation that has no such restrictions on it, though never say never in math, right? There could be some random cases where it doesn't work out. All right, so here's a quick review of first order linear differential equations. You could review section 2.3 before you go on. Otherwise, just stay tuned in and check it out. So recall the general solution of a linear first-order differential equation is a1 at x times y prime plus a0 at x times y equals to sum g at x. Now this can be rewritten if you divide through by that a1 and then rename that ratio a0 at x over a1 at x as p at x. You would get dy dx plus p at x times y is equal to some f at x, because that has now changed since we divided through by a1 at x. Assuming that p at x and f at x are continuous on a common interval I, using the integrating factor method, the general solution on the interval I was y equals c1 e to the negative integral p at x dx, and then plus e to the negative integral p at x dx times the integral e to the positive integral p at x dx times f at x, all with respect to x. Cool? And then that one also would have, notice that this solution has the same form as we have been working with. So it basically has y equals some complementary equation plus some particular solution, or complementary solution and a particular solution. So this part would be yc and this part would be yp. Cool? In this case, like I just said, sorry, yc equals c1 times e to the negative integral p at x dx is a solution of the associated homogeneous equation where we have dy dx plus p at x times y equals 0, and our yp, the particular solution was all of that other stuff, e to the negative integral p at x dx times the integral e to the integral positive p at x dx times f at x dx. Now this is a particular solution of the non-homogeneous equation dy dx plus p at x times y is equal to f at x. So let's rederive yp above by the method called variation of parameters. So fun! All right, so suppose y1 is a known solution of the homogeneous equation dy1 dx plus p at x y1 is equal to 0. Now, since y1 equal to e to the negative integral p at x dx is a solution, and because the equation is linear, c1 times y1 at x is its general solution. Variation of parameters consists of finding a particular solution of dy dx plus p at x times y equal to f of x of the form yp equals u1 at x times y1 at x. Now this requires us to replace the parameter c1 by a function u1. So it's actually really neat. We have dy1 dx plus p at x times y. That's equal to 0. Okay? Now, if we let yp, the particular solution, equal to u1 y1, let's see what we get. So we would have d dx of u1 y1 instead of we're doing our particular solution in there, plus p at x times u1 y1 is equal to f at x. So then, if you take a look, we would end up having, if we differentiate in there, we would have du1 dx times y1 plus u1 times dy1 dx plus p at x times u1 times y1 equal to f at x. Now, putting this together here, if I factor out a u1 from the second two terms, so I would have u1 times dy1 dx plus p at x times y1, and then I still have my du1 dx times y1 term equal to f of x. Remember that all of this here is assumed to be 0, right? From up there. So this actually simplifies to be y1 times d1 u with respect to x is equal to f at x. Now, this is just a separation of variables problem, so I keep du1 on the left side, and then I'll have f at x over y1, and then that's all times dx, and integrating both sides, we'll get u1 is equal to this integral f at x over y1 at x with respect to x. Now, yp, remember, is u1 y1, and so that would give us yp is equal to y1 times the integral we just found for u1. So we'll have f at x over y1 at x dx. Cool, cool. And here it turns out that if you take a look, this here, it matches up with this one over here. Groovy? Or we'll be utilizing that one. So, linear second order differential equations. Consider the case of a linear second order equation a2 at x times y double prime plus a1 at x times y prime plus a0 at x times y is equal to some g of x, which has the standard form if you divide it through by a2 at x and rename those quotients, we would have y double prime plus some p at x times y prime plus some q at x times y is equal to some f at x, where we assume that the coefficient functions p at x, q at x, and also f at x are continuous on some common interval I. Now, when the coefficients are constants, the complementary solution y sub c is yc equals c1 y1 at x plus c2 y2 at x. Now let's see if the parameters c1 and c2 in yc can be replaced with functions u1 and u2, also known as variable parameters, so that yp at x, which is equal to u1 at x times y1 at x plus u2 at x times y2 at x, is a particular solution of that standard form, which was y double prime plus p at x y prime plus q at x y is equal to f at x. Okay, so let's check this out. If we have, remember that y, if we have y, our particular solution yp at x is equal to u1 y1 plus u2 y2. Now the first derivative is going to be of this one, yp prime at x will be, and I'll go a little bit fast here, it'll be u1 prime y1 plus u1 y1 prime, that's for that first term, and then plus u2 prime y2 plus u2 y2 prime, that's for the second term. And then the second derivative will be yp double prime at x, and then again we just kind of go through u1 double prime y1 plus u1 prime y1 prime, that's for the very first term right here, and then continuing we'll have plus u1 prime y1 prime plus u1 y1 double prime. And then on to that third term, we'll have plus u2 double prime, y2, these are all product rules, plus u2 prime, y2 prime, and then plus u2 prime, y2 prime, plus u2 y2 double prime. All right, so I'm going to just leave those, I know that there's a couple of like terms in there, but I'm going to leave them out. There's a definite plan. All right, so now if I go back into, this standard equation and take a look at everything, just at the left-hand side, first of all, I will have y double prime, and then we want these in particular form. So yp, and actually let me put in the p's here, these should be particular. So for our particular solution, we will have u1 double prime y1 plus all right, so that was my y double prime at x. And then we have p of x times y prime. So just say plus p at x times u1 prime y1 plus u1 y1 prime plus u2 prime y2 plus u2 y2 prime. And then we have plus q at x times our yp. And our yp was just u1 y1 plus u2 y2. Good so far? There we go. Better. All right, now that in turn equals, so we're going to take a look at how we can group, creatively group some of these things. So I'm going to factor out a u1. All right, so if I factor out a u1, I'll have a y1 double prime from this term. And then the next time I have a u1 term is I have one over here, okay? And so then that would be plus p at x times y1 prime. And then I have another u1 term over with the q at x, so plus q at x y1. Cool so far? All right. Now, I want to factor out a u2. So I'll have y2 double prime. I'll have another one with the p at x. And then I'll have one over with the q at x. And you'll like what's coming. And then I have some leftover stuff, right? I have, let's see what I have left over. Let's start from the top. So we still have plus u1 double prime y1 plus u1 prime y1 prime plus another u1 prime y1 prime, we'll be using that, plus u2 double prime y2 plus u2 prime y2 prime and another u2 prime y2 prime. And we have a p at x times u1 prime y1. And we actually have another one. We could factor out that p of x, couldn't we? And then we'd have plus u2 prime y2. And then I think we have everything pretty much grouped. So let's see what we can get rid of. Now, do you see here, because of this premise, right, this homogeneous, the homogeneous equation, these guys are going to zero out. So we're going to have this term here is 0, and we're going to have this one here is 0, okay, under our assumptions. So this is going to simplify a bit, right? So we'll have continuing, we'll end up having y1 u1 double prime plus y1 prime u1 prime. What I'm doing is I'm grouping these. You're going to see that these are derivatives. So we'll condense them. And now looking at the y2s, we would have y2 u2 double prime plus y2 prime u2 prime. So we just went through and used all of these terms here, I think. Or not all of them, sorry. We have like a couple left over here. We used 1 and 2 and 1 and 2. There we go. So then we will have plus p at x times u1 prime y1 plus u2 prime y2. So y1 prime u1 prime plus y2 prime u2 prime. Okay, so this now ends up being the derivative with respect to x of. So if you look at the two parentheses above it, this is actually going to be y1 u1 prime for the first parentheses. The second parentheses, which is still being differentiated, would be y2 u2 prime. So all of this here is equivalent to this right here. Cool so far? And then plus p at x times r y1 u1 prime plus y2 u2 prime, y1 prime u1 prime plus y2 prime u2 prime. Okay, so assuming that u1 and u2 satisfy y1 u1 prime plus y2 u2 prime equals 0, then we have this would be 0, right? This guy would be 0. And what would we be left? We'd have this one left. And what's that going to equal? Good, f at x, right? Because that's what this whole thing right here was supposed to equal. All right, so now, we have the fact that y1 u1 prime plus y2 u2 prime is 0. And we also have that y1 prime u1 prime plus y2 prime u2 prime equal f at x. And with that, we can make up a system of equations, and we can use the Wronskian. So we'd have the denominator, the Wronskian for y1 and y2 would be, so this would be y1 and y2 would be y1 u1 prime y1 y2 y1 prime y2 prime. Isn't that cool? And then if we look at W1, looking at Cramer's rule, we would end up having, you replace whichever column whichever you're solving for. So if we were solving for u1 prime, we would replace that with 0 and f at x. We'd keep the y2 and the y2 prime. W2 would be keeping y1 and y1 prime, replacing the second column with 0 and f at x. And it's really cool because you end up with, from here, you end up with u1 prime is equal to w1 over w and u2 prime is equal to w2 over w. Isn't that cool? Now, we know w is the Wronskian of y1 and y2, right? And by linear independence, of y1 and y2, we know that the Wronskian of y1 and y2 is non-zero. So we're okay with the denominators there. And that's for any x which belongs to the interval I. Some math shorthand. All right, so steps for solving, right? We always like to have some steps, right? So find the complementary function if yc is equal to c1y1 plus c2y2. Compute the Wronskian. So w of y1 at x and y2 at x. Divide by a2, if it hasn't already happened, to put the equation in the standard form. y double prime plus p times y prime plus q times y is equal to f at x. And then we want to, and we do that because we want to determine what f of x is. We then integrate u1 prime, which remember was w1 over w, and u2 prime, which is w2 over w, to find u1 and u2. And then a particular solution is u1 times y1 plus u2 times y2. And then your general solution is equal to your complementary solution plus your particular. Now, as far as constants of integration go, constants do not need to be added when we find the indefinite integrals for u1 and u2, because we've got y is equal to yc plus yp, right? So then you have, some c1 y1 plus c2 y2 for your, remember we looked at that back here, for your yc. And then for your yp, you'll have some, maybe u1 plus a1, say, times y1, plus some u2 plus b1 y2. But, if you kind of group things together here, what'll happen is you'll get, so switching it up a little bit, you'd have something like this, c1 y1, I'm going to put them all the y1s together, plus u1 y1 plus a1 y1, and then we'll put the 2's together, c2 y2 plus u2 y2 plus b2 y2. Well, here, u is the function, c1 and a1 are constants, so you'd have like c1 plus a1 y1, you'd have c2 plus a2 y2, and then you'd still have u1 y1 plus u2 y2 hanging out for our functions. But a sum of constants is just a constant, so you'd have c1 y1 plus c2 y2 plus u1 y1 plus u2 y2. So that's kind of a long reason why you don't have to worry about it. Okay, so let's look at this first example. All right, so we want to solve each of these differential equations by variation of parameters. So here we go. We want to find yp, and note here, okay, that it's already in standard form, and so f at x is going to be tangent at x. So to find yp, we're just going to go back to what we were doing, solve m squared plus 1 equals 0. So we're going to get m squared is -1, and so m is going to be plus or minus I. So working on our auxiliary equation. So in something like this, you'd have like your m1 is 0 minus I, m2 is 0 plus I. And so when we were working with those other things, this would give us alpha 1 and 2 are 0, beta is 1. So what we'll have is, we'll have our yc is going to be c1 cosine x plus c2 sine x the beta goes with the angle. If we had had alpha something other than 0, we would have had e to the alpha x. That's back in a prior section. So hopefully you're cool with that. Now that's our complementary. So we've also got our f of x. So now we want to work with the Wronskians, okay? So working with our Wronskians, we can call y1 equal to cosine x. So y1 prime is going to be negative sine at x. And then y2 is sine at x. And y2 prime will be cosine at x. So that's what's going to make up the denominator Wronskian, right? So we'll have this one be the determinant going down cosine x, negative sine at x, and then sine at x, cosine at x. And when we find that, we'll get cosine squared at x minus a minus is plus sine squared at x, which is just equal to 1. So the denominator for our u1 prime and u2 prime will be 1, which is nice. Now, w1 is going to be, we are going to have 0 and f of x. So 0 and tangent x replace the first column. And then we'll have the second column stay the same. And so that's going to be 0 minus sine at x times tangent at x, which is equal to, now this one, we want to get this in a form that's easy to integrate, so we're going to play with this. This is equal to negative sine at x times sine at x over cosine at x. Cool so far? Which in turn is negative sine squared at x over cosine at x. Still not quite where we want it, because we would, if we were doing a u sub, it'd be the denominator, and that's not going to work. So we can rewrite sine squared at x as 1 minus cosine squared at x over cosine at x, more promising, which in turn will be negative 1 over cosine at x, because we have a single term in the denominator, and then minus cosine squared at x over cosine at x, which is cosine at x, which will give us negative secant at x plus cosine at x, which is cosine at x, minus secant at x, which we can integrate just fine. Cool, cool? And then our second Wronskian, I don't think is as bad. We'll have cosine at x, negative sine at x for the first column, 0 and f of x, which is tan x for our second one. And then that'll be cosine at x times tangent at x minus 0, which is, that will simplify because tangent at x is sine over cosine. So this is just going to be sine at x. Good so far? Awesome. All right, so u1 prime is w1 over w. Remember, w was just 1, so it's going to be cosine at x minus secant at x. Over 1, I'll just write it, which is cosine at x minus secant at x. So if I rewrite So if I rewrite this as like a d dx, I'll have du1 is equal to cosine at x minus secant at x dx. And then integrating both sides, I'll get u1 is equal to sine at x minus natural log absolute secant at x plus tangent at x. And I found u1. So now u2 prime is going to be w2 over w, which is sine at x over 1, which is just sine at x. So if I look at du2 is equal to sine at x dx and integrate both sides, then u2 will be negative cosine at x. Cool so far? So I've worked with the Wronskians, and then now this part is, find u1 and u2. So let's find yp. So yp is u1 y1 plus u2 y2. So in this case, our u1 is sine at x minus natural log absolute secant at x plus tangent at x. And then what was our y1? Remember, y1 way back when was cosine at x. This is all times cosine at x. And then u2 was actually negative, right? So minus cosine x times sine at x. Now notice we have a positive factor of cosine at x times sine at x when you distribute the cosine at x, so those will zero out. So we actually just get negative cosine at x times natural log absolute secant at x plus tangent at x for the particular. And then now find y. Well, remember, y is equal to yc plus yp. And so y is going to equal to, way back when, our yc was c1 cosine x plus c2 sine x. And then our particular is just minus cosine at x times natural log absolute secant at x plus tangent at x. And we're done. Isn't that cool? Cool process? Alright, sorry I sort of hid the next problem here. Alright, so next example. Y double prime minus 2y prime plus y equals e to the t times inverse tangent at t. So for this one, if you want to go ahead and pause the movie and try it yourself, that's fine. You've got the tools for it. Otherwise, just follow along. So we want to find yc. So the auxiliary equation is going to be m squared minus 2m plus 1 is equal to 0. And then we can factor that as m minus 1, the quantity squared, is 0. So we'll get m is equal to 1 with multiplicity of 2. So that gives us our complementary equation of e to the 1x for that first one. And actually, sorry, we need our constant. C1 e to the 1x plus C2x e to the 1x because of the multiplicity. All right. Now, this is already in standard form, and so f at x is equal to e to the t times, I'm going to write this as arc. I like the arc notation. It's the same, arc tangent at t. And you know what? I'm going to change these. I didn't realize it was in terms of t. I'm going to change these here to t's. Okay, so now we want to find our Wronskians. So we can let y1 equal to e to the t. So y1 prime will be e to the t. That's nice and easy. y2 is te to the t. And y2 prime will be 1e to the t plus te to the t, which is e to the t times 1 plus t. So our w will be e to the t to the t, te to the t, and e to the t times 1 plus t, which will equal to e to the t times e to the t is e to the 2t, and we'll have 1 plus t as a factor, minus te to the 2t. Now notice when you distribute, you'd have a positive 2e to the 2t, so the only thing left will be e to the 2t. And our w1 will be, we'll replace the first column with 0 and then e to the t, arc tangent at t, and then keep our second column the same. That's going to be 0 minus t e to the 2t, arc tangent at t, which is just negative t e to the 2t, arc tangent at t. All right, and then our second numerator will be, so we have e to the t, e to the t, and then we'll replace the second one with 0 and e to the t times arc tangent at t. That's going to give us e to the 2t times arc tangent at t, minus 0, which is just e to the 2t arc tangent at t. So now find u1 and u2. That's our next plan, part of our evil plan. So we know u1 prime is w1 over w, which is, w1 was negative t e to the 2t times arc tangent at t over e to the 2t. So the e to the 2t's divide out, and we'll end up with negative t times arc tangent at t. u2 prime is w2 over w, which is e to the 2t times arc tangent at t over e to the 2t. These will divide out, and we'll just have arc tangent at t. So now we have to integrate. So these are not the friendliest integrals, I don't think, on this one. We have to kind of do integration by parts on both. So let's take a look. U1, so du1 is going to equal to negative t arc tangent at t dt. So just change that prime notation and set these equal to each other. Now we need to integrate both sides. I'll keep that negative out. And let's do some side work. So U has to be arc tangent at t because that doesn't have a regular integral formula. So du is going to be dt over 1 plus t squared. dv will be equal to t dt, and so v is going to be t squared over 2. So now my integral is going to be, remember it's u times v, right? So u times v will give me t squared over 2 times arc tangent at t minus the integral of v du. So t squared over 2 times dt over 1 plus t squared. And oh, what fun! Within this, we get to do long division, right? So I'll do that above. Make a little line here. So I'll write it as t squared plus 1 is the divisor going into t squared plus 0t plus 0. So that'll be 1. We'll have t squared plus 1. When I subtract, I'll just get a negative 1 remainder. So this will be 1 minus 1 over 1 plus t squared. So we will have t squared over 2 arc tangent t minus, I'm going to take out that 1/2, and then we're going to have the integral of 1 minus 1 over 1 plus t squared dt. This is our integration by parts, and this was our long division. All right, so that will be t squared over 2 arc tangent at t minus 1/2 times t plus 1/2 times arc tangent at t. A minus a minus. So I will get u1 equals negative. I'm going to say arc tangent at t over 2. Actually, I don't need this parenthesis. I'll put a grouping symbol. Arc tangent at t over 2. And then I would have t squared plus 1, and then minus 1/2 t. But we've got that negative symbol, so u1 will end up being negative arc tangent at t over 2 times t squared plus 1 plus 1/2 t. Well, that one was wild, huh? All right, now du2 equals arctangent at t. So still an integration by parts, but not as bad. And then we have our dt. So when I integrate, my next one will be u is arctangent at t, du is dt over 1 plus t squared, dv, this one's tricky, is just dt, so v equals t. So u times v will give me t arctangent at t minus the integral of v du, so t times dt over 1 plus t squared. So we'll have t arctangent t minus integral of t over 1 plus t squared dt. Now to integrate that, the derivative of the denominator is 2t, so I need a 2t dt. So I'll balance it out with that 1/2. And then we'll get t arctangent at t minus 1/2 times natural log of 1 plus t squared. Crazy, huh? All right, so plugging that one in, and this would be my u2 over here. So now we can find our particular solution. So if we find yp, right? So this part, we want to, yp, remember, is u1 y1 plus u2 y2. So yp will be u1, different color here. So my u1 was negative arctangent at t over 2 times t squared plus 1 plus 1/2 t. And then y1, way back here, was e to the t. And then plus t arctangent t minus 1/2 natural log 1 plus t squared. All of that will be times t e to the t, because that is what y2 was. Cool, cool? All right, so find the general solution. Well, remember our general solution is y equals yc plus yp. So our yc from many moons ago was c1 e to the t plus c2 t e to the t. Now we'll do our particular. So actually I'll write it as minus e to the t times arctangent t over 2 times t squared plus 1 plus t over 2 And then we'll have plus t e to the t times t arc tangent at t minus 1/2 natural log at 1 plus t squared. And that is our general solution. All right, hang in there. I know this one's a long one. Okay, so our next example is finding, doing the whole thing, finding the solution, and then also utilizing the initial conditions. Y at 0 is 1, y prime at 0 is 0. So let's check it out. So you go through the same steps. So you find YC. So in this case, we'll have m squared minus 4m plus 4 is 0. So we'll get m minus 2, the quantity squared is 0. m1 equals m2 equals 2. So YC has got to be what? Beautiful. E to the 2x, these are x's, right? And then we have a C1 in front of it plus C2 xe to the 2x. Cool so far? All right. Now, it's already in the standard form. So this is our f of x, so we found that. And then we got to deal with our Wronskians. So, working with y1 is just, we'll do e to the 2x. y1 prime is 2e to the 2x. y2 is xe to the 2x. And y2 prime is 1e to the 2x plus 2xe to the 2x. So y2 prime, if you factor out that e to the 2x, you're going to get 1 plus 2x remaining. So our w will be e to the 2x, 2e to the 2x, xe to the 2x, and then e to the 2x times 1 plus 2x. And that will be e to the 4x times quantity 1 plus 2x, and then minus 2x e to the 4x. So notice that you'll have a positive 2x e to the 4x and a negative 2x e to the 4x. So they will zero out, and we will just have remaining e to the 4x. And our w1 will be, so we replace 0 and our f of x, which is 12x squared minus 6x times e to the 2x in our first column. And then we'll have our xe to the 2x and e to the 2x times 1 plus 2x as the second column. That's going to be 0 minus xe to the 4x times 12x squared minus 6x, which of course is just negative xe to the 4x times 12x squared minus 6x. All right, and w2 will be e to the 2x, 2e to the 2x, and then 0 and 12x squared minus 6x times e to the 2x. That's going to be e to the 4x times 12x squared minus 6x minus 0, which will just be e to the 4x times 12x squared minus 6x. Cool so far? Alright, so we got all the Wronskians out of the way. Now we need to find u1 and u2. So, to do that, remember that u1 prime is w1 over w, which is going to be negative x e to the 4x times 12x squared minus 6x all over e to the 4x. So the e to the 4x's divide out, and we'll end up getting, let's see, when you multiply it through and swap the sign, it'll be 6x squared minus 12x cubed. I multiplied the x in through there and flipped the signs. And that one, fortunately, is nice and easy to integrate. Let's actually go ahead and do that now. So we'll have du1 equal to quantity 6x squared minus 12x cubed dx. And integrating both sides, we'll get u1 equals 6x cubed over 3, which is 2x cubed, and then 12x to the 4th over 4, which would be minus 3x to the 4th. That's nice after that last one, right? All right, and our u2 prime is w2 over w, which is e to the 4x times 12x squared minus 6x over e to the 4x. The e to the 4x's divide out, and we'll just have 12x squared minus 6x. And du2 equal to 12x squared minus 6x dx is going to be, when we integrate both sides, u2 will equal to 12x cubed over 3 will be 4x cubed. 6x squared over 2 will be minus 3x squared. Cool, cool? All right. So now, finding our particular, remember yp is u1 y1 plus u2 y2. So we will have, so yp will be, let's see what our u1 was, 2x cubed minus 3x to the 4th, and that's going to be times e to the 2x. That was our y1, plus 4x cubed minus 3x squared times x e to the 2x, which was our y2. We can clean that up a little bit. That would be 2x cubed e to the 2x minus 3x to the 4th e to the 2x plus 4x to the 4th e to the 2x minus 3x cubed e to the 2x. So yp will be x to the 4th e to the 2x minus x cubed e to the 2x. Or x cubed x e to the 2x minus 1. X cubed e to the 2x times x minus 1. Cool, cool? All right, now find the general solution. So y equals yc plus yp. So if you recall, yc was c1e to the 2x plus c2 xe to the 2x. And then our yp is x cubed e to the 2x times x minus 1. Now, let's apply our initial conditions. So, initial conditions. So, y at 0 was equal to 1, and y prime at 0 is 0. So, y at 0 is 1, y prime at 0 is 0. So, we found y. So, 1 would be, wherever I see an x, I'll put a 0 for this equation here. So 1 would be c1 e to the 2 times 0 plus c2 0 times e to the 2 times 0 plus 0 cubed e to the 2 times 0 times 0 minus 1. So we will get, after all is said and done, that c1 is 1. Now we need to find y prime, right? We don't have it. So y prime is going to be 2c1 e to the 2x plus c2 e to the 2x plus 2c2x e to the 2x, and then the last term we'll have, do one at a time, so we'll have plus 3x squared e to the 2x times x minus 1 plus x cubed times 2 e to the 2x times x minus 1 plus x cubed e to the 2x times 1. And we know that y prime at 0 is 0, so if I put in 0 for y prime, I'll have, do you see that all of the terms except for the first two will zero out when x is 0? So I'll end up with 2 times c1 plus c2. And that's equal to 0. And so C2 is 2 times 1. It would be negative 2 times 1, sorry. So we'll have C2 is negative 2. And then finally, drum roll, our solution will be y equals C1 was 1, so we'll have e to the 2x minus 2x e to the 2x plus x cubed e to the 2x times x minus 1. And we're done with that one. All right, just a little bit more here. I know this is a pretty long one, intense section. Integral defined functions. When we encounter non-elementary integrals while computing our solution method, we just use the integral defined functions. u1 at x is equal to negative integral x0 to x, y2 at t f at t, these are from the Wronskians, over w at t dt, and u2 at x would be integral x0 to x, y1 at t, f at t, over w at t dt. With the assumption that the integrand, so this is like w2 over w in terms of t, and the first one was w1 over w in terms of t. And this is the assumption that the integrand is continuous on the interval from x0 to x inclusive. So this third example, let's go ahead and take a look at it. Fortunately, this is our f of x, so we don't have to find it. So let's find yc. So when we find yc, m squared minus 4 is equal to 0. M squared is equal to 4, so m1 would be negative 2, and m2 would be 2. So yc is just c1 e to the negative 2 plus c2 e to the positive 2x. And now our Wronskians. So we have y1 equal to e to the negative 2x, y2 equal to e to the 2x. So y1 prime will be negative 2 e to the negative 2x. y2 prime is 2e to the 2x. And so w will be e to the negative 2x, negative 2e to the negative 2x, first column, and then e to the 2x and 2e to the 2x, second column. And then that's just going to be 2 minus negative 2, which is, and w1 will be replacing the first column with 0 and f of x, which is e to the 2x over x. And then we still have our e to the 2x and our 2e to the 2x. That's going to be 0 minus e to the 4x over x, which is negative e to the 4x over x. w2 will be e to the negative 2x, negative 2e to the negative 2x, and then 0 and e to the 2x over x, which will be 1 over x minus 0, which is 1 over x. Cool, cool? All right. So now, to find u1 and u2, u1 prime is w1 over w, which is negative e to the 4x over x over 4, which will be negative e to the x over 4x. Now this is not an elementary integral, so when you can take out your negative a quarter the integral e to the x over x with respect to x, it's something you have to do numerically. So, integrating both sides, we have u1 equals negative 1/4 integral from x0 to x e to the t over t dt. Cool? Now, u2 is something we should be able to find. So u2 prime is going to be 1 over x over 4, because that was from our Wronskian. So w2 over w, which is 1/4 times 1 over x. So du2 equal to 1/4 times 1 over x. We can integrate, and we get u2 is 1/4 natural log absolute x. So our particular solution is yp is u1 y1 plus u2 y2, and where are our y's? E to the negative 2x and e to the 2x. So we have yp is negative 1/4 integral x0 to x e to the t over t dt times e to the negative 2x, and then plus 1/4 natural log absolute x times e to the 2x. So our general solution will be y equals yc plus yp. So y will equal to, we had c1 e to the negative 2x plus c2 e to the 2x, and then our particular, which will be minus e to the negative 2x over 4 times the integral from x0 to x of e to the t over t. You know what? Just some changes. That should have been e to the 4x, which would make these all 4s. Yes. So that would make this 4t. My apologies. And I think I fixed them all. Okay. And then dt plus e to the 2x over 4 times natural log absolute x. We're all done. So for this next example, the indicated functions are known linearly independent solutions of the associated homogeneous differential equation on 0 to infinity non-inclusive. So we want to find the general solution of the given non-homogeneous equation. So let's do a couple things here. First off, we want to divide both sides by x squared to get this in standard form. So this is going to be y double prime plus 1 over x y prime plus 1 over x squared y is equal to secant at natural log x over x squared. Now, since we know those are our solutions, we also know that to find yp, all we have to do is put the associated constants, right? So not yp, yc. So yc will be equal to c1 cosine at natural log x from y1 plus c2 sine at natural log x. Now, let's do our Wronskians. So, y1 is cosine at natural log at x, and y1 prime is going to be negative sine at natural log at x over x. y2 was sine at natural log at x, and so y2 prime will be cosine at natural log at x, and then using that chain rule times 1 over x. So w equals cosine at natural log at x and negative sine at natural log at x over x, and then sine at natural log at x, and then we'll have cosine at natural log at x over x. So w will be cosine squared at natural log at x over x, minus a minus is plus sine squared at natural log at x over x, which, beautifully enough, will just be 1 over x, because cosine squared plus sine squared is 1, and they both have the same denominator. So w1 is going to be 0, and then we'll have what? Secant at natural log at x over x squared. And then we'll still have the second column the same. So that's going to equal to 0 minus sine at natural log at x times secant at natural log at x over x squared. And that is just tangent, negative tangent at natural log at x over x squared, because that's sine over cosine. So then our second Wronskian will be cosine at natural log at x, and then negative sine at natural log at x over x, and then 0 and secant at natural log at x over x squared. That will equal to cosine at natural log at x times secant at natural log at x all over x squared minus 0. Oops. And this is actually, believe it or not, just going to be 1 over x squared. All right, so now we need to find u1 and u2. So let's check it out. So remember, u1 prime is w1 over w, which is negative tangent at natural log at x over x squared, and then over 1 over x. So this will end up being negative tangent at natural log at x over x. Which is nice because it's all ready for integration. So du1 equal to negative tangent at natural log at x over x. 1 over x is the derivative of what's inside the trig function. So we're good to go on the integration. We'll just get u1 is equal to negative natural log absolute cosine at natural log at x and the negatives will go away and we'll have natural log absolute cosine at natural log at x. And then u2 prime is, of course, w2 over w, which will be 1 over x squared over 1 over x, which is just 1 over x. And so this one will be nice and easy for integration. We'll have du2 is 1 over x dx, and integrating we'll have u2 is natural log at absolute x. So our particular solution, find yp, right? We'll just have yp equals u1 y1 plus u2 y2. So yp will be, let's see, our y1 I think was cosine of natural log at x. So this will be cosine at natural log at x times natural log at absolute cosine at natural log at x plus, let's see, u2 was positive, so plus sine at natural log at x times natural log absolute x. And then the general solution will be y equals 2 c1 cosine, c1 cosine at natural log at x plus c2 sine at natural log at x, and then plus our particular, which is cosine natural log at x times natural log absolute cosine at natural log at x plus sine at natural log at x times natural log absolute x. And that's it. So gave us, I guess you could call it a shortcut. All right, higher order equations, and this is it. Just a little bit of background and then an example, and then we're done. So we can generalize this method for non-homogeneous second-order linear differential equations to linear nth-order equations that have been put into the standard form, the nth derivative plus some p sub n minus 1 at x times the n minus first derivative of y plus dot 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 plus p1 at x y prime plus p0 at x times y equals to some f of x. If yc equals c1 y1 plus c2 y2 plus dot 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 plus cn yn is the complementary function for the equation above, then a particular solution is yp at x equals u1 at x, y1 at x, plus u2 at x, y2 at x, plus dot dot dot, plus un at x, yn at x, where the u sub k prime, where k equals 1, 2, all the way down to n, are determined by the n equations. So you basically have your y1 u1 prime plus y2 u2 prime plus dot 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 plus yn un prime equals 0. Then it goes y1 prime u1 prime plus y2 prime u2 prime plus dot 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 plus yn prime un prime equals 0. You just keep going like that until you get to y, the n minus first derivative of y1 times u1 prime plus the n minus first derivative of y2 times u2 prime plus dot 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 plus the n minus first derivative of yn times u sub n prime. This one would equal to some f at x. So these would go all the way down. They'd be all zeros except for that last one. Now, the first n minus 1 equations in this system are assumptions that are made to simplify the resulting equation after yp equal to u1 at x, y1 at x, plus u2 at x, y2 at x, plus dot dot dot, plus un at x, yn at x, is substituted in that nth derivative of y plus p sub n minus 1, and then the nth, that's at x, times the n minus first derivative of y plus dot 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 plus p1 at x, y prime, plus p0 at x, y equals f at x. Now, Cramer's rule gives that uk prime is going to be wk over w, where k goes from 1 to down to n, and where w is the Wronskian of y1, y2, all the way down to yn, and wk is the determinant obtained by replacing the kth column of the Wronskian by the column consisting of the right-hand side. So all of this stuff. Or think of the column consisting of 0, 0, dot, 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 0, and then f of x would be that last bit. So when n is 2, we get that u1 prime, like we were working with, is w1 over w, and then u2 prime is w2 over w. When n is 3, you'll get a particular solution. Yp is u1 y1 plus u2 y2 plus u3 y3, where y1, y2, and y3 are a linearly independent set of solutions of the associated homogeneous DE. And u1, u2, and u3 are determined from u1 prime is w1 over w, u2 prime is w2 over w, and u3 prime is w3 over w, where, of course, w equals. So you'll have y1, y1 prime, y1 double prime, y2, y2 prime, y2 double prime, and y3, y3 prime, y3 double prime. So when you're on w1, you're going to replace the first column with 0, 0, and then your f of x. And the other two are the same, so you'd have y2, y2 prime, y2 double prime, y3, y3 prime, and y3 double prime. w2 will be y1, y1 prime, y1 double prime, then 0, 0, f of x, and y3, y3 prime, and y3 double prime. And finally, we're just going to w3 equals y1, y1 prime, y1 double prime, y2, y2 prime, y2 double prime, and then 0, 0, and f at x. Cool? All right, so now we come to our last example, 5. Please solve the given third-order differential equation by variation of parameters. And this time we've got it already in standard form, which is nice. Y triple prime plus 4y prime is secant at 2x. So secant at 2x is our f of x. And then we need to go through all our steps, find yc. So that's going to be m triple prime plus 4m m cubed plus 4m is 0. M times m squared plus 4 is 0. So we'll get m1 is 0. And then m2, this will be complex, so we'll get negative 2i. And m3 is positive 2i. So for these, our alpha is 0, e to the 0x, so we don't have that exponential term. And then beta is 2, the coefficient to the angle. So our yc will be c1 for the 0, m1, and then plus c2 cosine of 2x plus c3 sine 2x. Cool? All right. So that's going to give us, of course, that y1 is some constant. Just call it 1. y1 prime would be 0. I'm setting up our Wronskian. y1 double prime is 0. Y2 is cosine at 2x. Y2 prime is negative 2 sine at 2x. And y2 double prime will be negative 4 cosine 2x. And then y3 will be sine at 2x. y3 prime is 2 cosine at 2x. And then y3 double prime will be negative 4 sine at 2x. So now, making our Wronskians. Starting out with W. So W will be 1, 0, 0, cosine 2x, negative 2 sine 2x, negative 4 cosine 2x. And then we have sine 2x, 2 cosine 2x, and negative 4 sine 2x. So it won't be so bad because of all these zeros. So I'm going to expand about this column. And so that's going to give us 1 times negative 2 sine 2x, 2 cosine 2x going across, negative 4 cosine 2x, and negative 4 sine 2x. And the other two will zero out. So now this is going to end up being 8 sine squared 2x plus 8 cosine squared 2x. You factor out an 8, you'll just get 8 times 1. So this is just 8. It's nice. W1 will be replacing the first column with 0, 0, and then secant at 2x. And I'll go ahead and expand again about that easiest row, or column rather. So that's going to be positive secant at 2x times cosine 2x, sine 2x going across, and then negative 2 sine 2x and 2 cosine 2x. Now that's going to give us secant at 2x times two cosine squared at 2x plus 2 sine squared at 2x. And that, again, if you factor out the 2, it'll just be equal to 2 and then times secant at 2x. All right, and then W2 will be 1, 0, 0, and then replacing with 0, 0 secant 2x, and then sine at 2x, 2 cosine at 2x, and then negative 4 sine at 2x. And then we'll have, expanding again about our favorite column here. So that will be 1 times 0 to cosine 2x, and then secant 2x and negative 4 sine 2x, which will be 0 minus 2 cosine 2x times secant 2x, which will just be equal to negative 2. Looking good here. And then W3 will be 1, 0, 0 cosine 2x, negative 2 sine 2x, negative 4 cosine 2x. And then replacing the last column with our 0, 0, and secant 2x. And expanding about the first column again, we'll get 1 times the determinant, negative 2 sine 2x, 0 going across, negative 4 cosine 2x, and then secant at 2x. And that's going to give us negative 2 times sine at 2x times secant at 2x minus 0, which is just going to be equal to negative 2 tangent 2x. All right, making some progress. So now we want to find u1, u2, and u3. So u1 prime is w1 over w, which is going to be, w was 8, and so 2 secant 2x over 8. Which will be 1/4 times secant at 2x. And then to integrate that, so we'll have du1 is equal to 1/4 times secant at 2x dx. And then we integrate, I'm just pulling that constant out. In order to integrate, we have a 2 as a multiplier to that angle, so the derivative of that is 2. So we're going to need to balance it by 1/2. So then we'll get u1 is equal to 1/8 times natural log absolute secant 2x plus tangent 2x. And then u2 prime is w2 over w. w2 was negative 2, so this will be negative 2 over 8, which is negative 1/4. Nice easy one, huh? So we'll have du2 is equal to negative 1/4 dx, and integrate u2 is negative 1/4 x. u3 prime is w3 over w, which is negative 2 tangent 2x over 8, which will give us negative 1/4 times tangent at 2x. So not too bad of a derivative or an antiderivative to find. We'll have du3 is equal to negative 1/4 tangent at 2x dx. Integrating, we'll have, again, we need to balance this so that we can integrate just using pattern recognition. So u3 is equal to negative 1/8 times negative natural log absolute cosine 2x. And so that will end up being positive 1/8 natural log absolute cosine 2x. Wow, we're doing this thing, right? Okay, so now let's find our YP. So remember that YP is U1 Y1 plus U2 Y2 plus U3 Y3. So we had just let Y1 be 1. So U1 was what? 1/8. So YP will be 1/8 natural log absolute secant 2x plus tangent 2x. And then our Y2 was cosine 2x. And then U2 was negative 1/4 x. So we'll have negative 1/4 x times cosine 2x. And then our Y3 was sine 2x. And U3 was 1/8 natural log cosine 2x. So that would be plus 1/8 sine 2x, and then natural log, let's put these in parentheses, natural log absolute cosine 2x. Cool. And then finally our particular, so our general, find the general solution. So that's just y equals yc plus yp. So y equals, we had c1 plus c2 cosine 2x plus c3 sine 2x. And then our particulars, right? So we've got 1/8 natural log absolute secant x plus tangent x minus 1/4 x cosine 2x, and then plus 1/8 sine 2x natural log absolute cosine 2x. And we're all done. All right. Well, I hope you have a wonderful morning, afternoon, or evening whenever you're watching this show. And if you like what I'm doing, hey, hit that like button and subscribe. Bye.